Alright, so this time it's your turn. We have two networks here. So pause the video and construct a closure table for each of the following networks and determine the required conditions for the network to be closed. Alright, so let's start with the first one. So first, we have to rewrite this into a proposition. So we have switch P in series with the parallel network with not P and Q. So therefore, we can have this as P series end, but this is a parallel of not P or Q. So therefore, we need to find the closure table using this proposition. So we would have P and Q, and that would only mean we only have four different combinations of truth values. Then let's write the proposition and not P or Q. So first, let's write our truth values. Alright, there we go. And let's copy that to our simple propositional variables in the actual statement. We have a not p, so let's negate these ones. So we'll have 0, 0, 1, and 1. Alright, so first we have to find the truth value of the disjunction because it's the entire disjunction that is conjuncted to p. So we need to find the truth values of the entire disjunction first. So let's use a different color here. This is a disjunction, so as long as 1 is true, the entire disjunction will be true. So there's 1 here, that is true. No 1, this is false, true, and true. So these are now the truth values that we would need to see if they are conjuncted with P. So 1 and 1, that's true. 1 and 0, we know that's false. 0 and 1 is false. 0 and 1 is also false. So there we go. There's only one here that this is true. So now let us see. So as you can see, of course, if both switches are closed, so let's illustrate that if both switches are closed, then current will flow through P. And once it goes up, it will not flow here because this is open, because P is closed, not P is open, but Q is closed, so therefore current will flow. Hence, the network is closed if all switches are closed. However, take a look at the other values. Both got open or false here. And if we're going to analyze as well, if Q is open here, if Q is open, as what it says here, current cannot flow anymore because if this is closed, this is open and this is open. So current cannot flow anymore. So this is open. Similarly, if P is open right at the start, current cannot flow anymore. So this is already open. And same, P is still open here, so this is still open. So as you can see, the truth values in our table gave us an idea, gave us a hint that this is the only way that the network will be closed if both switches are closed. Alright, so now let's analyze the second one. But as you can see, there's actually 3 variables, so we might need a longer table. So I'll bring this down and I'll start my table here. Alright. But first, we need our proposition. So we have here 2 parallel networks. We have here not P or Q, and we have here not R or Q. Both in series, so therefore they would be not P or Q and not R or Q. So this will be our proposition. So let's just write that down. So we would have this here. We have 3 main propositional variables. So therefore we shall have P, Q, R. Then let's just have that down. There you go. Then let's write our statement. This is not P or Q, and not R or Q. So there we go. And let's write our values. Again, I'm going to go with my method here. Not required, but for me, this is the best way to double check that I've got all possible values. So there you go. And I'm going to copy as well the values and the basic ones. 0, 0, 1, 1, 0, 0, and 0, 0, 1, 1, 0, 0. So we have not P here, so we're going to negate the column of P. So I'll have 0, 0, 0, 0, 1, 1, 1, 1. And not R, we're going to negate this one. So we're going to have 0, 1, 0, 1, 0, 1, 0, 1. Alright, so now we can find the disjunction values here. So we're going to use a different ink this time. So as long as there is 1, the value will be 1. So this is true, 1. This is also 1. This is 0, 0, 1, 1, 1, and 1. Similar here because this is also a disjunction. So as long as there is 1, this will become 1, 1. This is 0, 1, 1, 1, 0, then 1. Then finally, our conjunction here, 1 and 1 is 1, 1 and 1 is 1, 0 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1. So let's see as to when this proposition, or this network rather, will be closed. So obviously, if all are closed, as you can see here, let's also take a look at the diagram. So here you go. So as you can see, if all are closed, P will be open, but Q will be closed, so the current can flow here. Then, if R is closed, not R is open, but Q is closed, so it can still flow here. So therefore, the network is closed if all the switches, if the values of P, Q, and R switch are closed. So for the second one, R is open and the two are closed. So not P will be open, so current can still flow here. Current can flow through Q, but as well current can flow through not R as R is open. So not R is closed. So this is also closed. Here, Q is open. So in this case, if Q is open, current cannot flow here, and if P is closed, not P is open, current cannot flow here. So this is already open. And analyzing all of those, these are the following conditions wherein the statement is closed. So this is also where the network is closed here, and we would also have here the network is closed here, and also the network is closed here. So those are examples of how we can analyze our switching network using propositions and truth tables.